Okay, we're going to continue the review with question number 5, and I want you to check that the two functions are inverses by using composition. So what that means is you want to check and see if two functions are actually inverses. When you do their composition, they should be undoing each other because they reverse each other, and you will get x. And it needs to work both ways. So you need to do both of those compositions and make sure that you're getting your x. So we're going to look at f composed with h. We don't know that they're inverses, but it wants us to check and see if they are. So we're going to do this composition. So remember, this means that we're going to look at h of x and plug it into function f. And so what that will look like, h of x is x plus 3 over 7. And so we have to plug that in to function f. Well, function f says your input has to multiply by 7 and minus 3. So we're going to have 7 times that input minus 3. So I'm going to stick that right inside where our x value was. Now what's nice here is that the 7s will cancel, and then you're going to end up with just x plus 3 minus 3, and so then the 3's will cancel, so everything undoes, and you're just left with x. So it seems like they're inverses, but we still need to check the other direction, which means h composed with f of x. So now we're going to take f of x and input that into h. So that will look like h of our f of x function is 7x minus 3. So now we're going to plug in to that x value our 7x minus 3. So the h of x function takes an input, adds 3 to it, and then divides by 7. So our input is that 7x minus 3. So when we try and simplify, you can see the minus 3 and plus 3, those undo each other, and you're just left with 7x over 7, but the 7's will be able to reduce, and you're just left with x. So again, because you were able to show that their compositions, both ways, end up getting you that x back, you know that they reverse each other, and so yes, they are inverses. Next, we're going to look at question 6, which is graphing a logarithm. So if we want to graph a logarithm, well, there's a couple transformations that are happening, so I'm going to point those out first. This is going to be moving my whole graph to the right one space because it's inside, affecting my x values. This is going to move my whole graph down 3, just like our previous transformations did to our basic functions. And so now we're going to look at our basic function being that log function. For me, it's easiest to graph the inverse of log, which the inverse of log is y equals 3 to the x. So if I think about not graphing this, but making the table for it, then I'll just switch my x and y's to have a table ready for my parent function. So for the inverse, 3 to the x, if I plug in, let's see, 1, 0, negative 1, those are my nice values. 3 to the 1 is 3, 3 to the 0 is 1, and 3 to the negative 1 is 1/3. So that means for my parent function, y equals log base 3 of x, without really doing too much work, I know the table will have a 3, 1 in it, a 1, 0, and 1/3 negative 1, because all I have to do is interchange those x and y since it's the inverse of that 3 to the x function. And so to graph, I'm going to start by putting my parent function on here. Let's put some marks. So my parent function will be at 3, 1, 1, 0, and then at 1/3, it'll be at negative 1. And so we're going to have the graph, remember, that's going to get closer and closer and closer to the y-axis. This one has a vertical asymptote, but not touch it. So that's my log base 3 of x. So now I have to use my transformations, which said move it right 1 and down 3. So first thing I'm going to move is the vertical asymptote. So if it moves right 1, it's going to now be at x equals 1. And all my points are going to also move right 1 and down 3. So in particular, the point 1, 0, moving it to the right 1 and then down 3 puts me here. This guy moving to the right 1, and then down 3, 1, 2, 3, puts me here. And so it's going to be the same shape as the green graph, but it's just been moved right 1 and down 3. So this is the graph of log base 3 of x minus 1 minus 3. Besides the asymptote, it also wants us to state our domain and our range. So the domain for this function is going to be from 1 to infinity, not including 1. And even without the graph, that should make sense because we only want to take log of positive values. That always has to be a positive value because that's always the answer to some exponent. The range for this function, that's going to be all real numbers from -infinity to infinity. Okay, next we're going to look at the graph of y equals 3 to the x minus 4 minus 1. We're going to identify the transformations again. This is moving us to the right 4, and that's because it's affecting my x values, which is the horizontal movement, and the minus 1 is going to move me down 1 space. So my basic function, y equals 3 to the x, that's an exponential function. I'm going to just make a table for that. There's no inverse that we need to talk about. We're not talking about log or anything, so I'm just going to plug in to find my parent function, just in case you're not sure of what it looks like. And so we get these points, which should all be really familiar since we've been graphing this function a lot. Put some key points on here. So at 1, I'm up at 3, 0, I'm up at 1, and -1, I'm at 1/3. And so here's my parent function, sketching it with a dotted line, kind of dotted, and it has a horizontal asymptote going on. So this is my 3 to the x function. And so if we're going to shift right 4 and down 1, that's going to make my horizontal asymptote now at -1. So y equals -1 is my horizontal asymptote. Now all my points are going to have to move right 4 and down 1. So in particular 0, 1, moving to the right 4, 1, 2, 3, 4, and then down 1 space. This guy moving right 1, 2, 3, 4, and then down 1 space. It should be the same picture as the green one, but just kind of slid to the right and down. So this is the graph of 3 to the x minus 4 minus 1. Now our exponential functions have domain -infinity to infinity, because remember they're the inverse of our log function. So compared to up above, which had a range of -infinity to infinity, this has a domain that way. Our range is going to be from -1 to infinity, because that's the lowest it will go because of that horizontal asymptote. All right, we're moving on to number 8. The first question is that it wants to know if this is 1 to 1. So 1 to 1 means that for every y, there's exactly one x. And so I want to check that. Well, one quick way is using the horizontal line test. So it's like the vertical line test, but horizontal. And the reason why it works is similar to the vertical line test, but we're looking at the inverse being a function, which goes the reverse way. So every y goes to x's, so we want to make sure every y has exactly one x. And this is a 1-to-1 function because it looks like it's the cube root of x, and it does pass the horizontal line test. It just has a little transformation going on. So it wants to graph both of these functions. So I'm going to graph both of these guys. So starting with our h of x, it's that cubic function shifted to the right 5 spaces. So it's going to be sitting right here. I'm going to draw its structure. And there's our little sketch. So this is h of x. Now it wants us to find the inverse and also graph that. So there's a couple of different ways that you could find the inverse. So one way is to think about it like in words. So function h wants you to take an input -5 and then cube root. So that's what function h is doing. the reverse way would have to undo each of those operations. So the opposite of cube rooting is going to be to cube, and then we're going to add instead of minus the 5. So that's going to be what H inverse is. So an equation would be H inverse of x equals x to the third power plus 5. So this is what my inverse function would be just based off of the words. Now the other way that some people like to do it, and you had to do it on some of our homework we've had, is to actually interchange the x and the y. The reason we had to do it in our homework is because we had an x value appearing in more than one place. So here we only have it in one place, so that's why the words worked. But I'll show you the algebra too. So we want to solve for our y. Once we interchange our x and our y, we want to solve for y. So to do that, we would want to undo the cube root, which would be by cubing both sides. So we're going to have x to the third power equals, the cube and the cube root will cancel out. So we'll be left with just y minus 5. And then we're going to plus 5 to both sides of my equation. So that's x to the third plus 5 is equal to y. So you can see it gets the same function. So if we want to sketch this guy, now remember the cube function, that one is more vertical because it grows much faster than the cube root function. And the plus 5 is going to move us up 5. So 1, 2, 3, 4, 5. We're going to be right there. We'll do our structure, those 3 points, but again, it's going to be growing vertically. And remember that all of the time, our inverse and our regular functions will reflect over the identity function, which is the line y equals x. You can also double check that you're like on track. The coordinates of each of these points should be interchanged. So if this is like 5, 0, then you better have 0, 5 on your graph, which you just do. And you can kind of mirror some of those other points as well. So for number 9, a lot of these can be done with a calculator, but I want you to show your work, meaning show me why it is what it is. So for the first one, we have to remember that a logarithm is an exponent. So this is saying 5 is my base, and I want to know what power will get me the 25. And so the answer to that question, our question mark, will have to equal a 2. So that means log base 5 of 25 will equal 2. For the next one, we're looking at a base of 25. So this time it's saying 25 to some power has to equal 5 this time. So the only way that a number can go from being big to something smaller like that is some sort of rational exponent. So in fact, this is going to be 1/2, because 25 to the 1/2 power equals the square root of 25, which is the 5. So next we're looking at a base of 2. And we want to know what power to put on that guy. That will make me get 1/8. So now we're getting a fraction. So we got smaller, but we also got a fraction. So we need to remember that fractions often will happen if we have negative exponents. And if we think about the number 8, that's from 2 times 2 times 2. So a -3 would work, since 2 to the -3 means 1/2 to the third, which is 1/8. The next one, this one you can kind of look at and you see that you have a base of 4, and then you have this exponential thing that also has a base of 4. Since we talked about that a log is the inverse of an exponential, these basically cancel each other out, and so we're just left with an answer of 11. If you want to write out what's happening, we could also say that this is a base of 4, so you can clearly see 4 here, and we want to know what the power is, because that's what a log is. That will get us 4 to the 11th. So the only thing that question mark could be is that 11. The next one we have natural log of e to the a. There's a few different ways to think about this, but when I see this natural log of e, I think about it as log base e of e to the a. And again, these bases are matching each other, but if you don't see it, we can rewrite it. E is our base, use our base here. We want to know what the exponent has to be that will make us have e to the a. And so the answer to that question, our question mark, has to equal that a. All right, for number 10, we're looking at the domain. Domain is what all the possible x's can be. So if we're looking at part A, we have a fraction. And when you have a fraction, the only thing that is a problem, because that's kind of what we're looking for. Domain, we normally assume it's like negative infinity to infinity unless there's some sort of problem. And the problems that we have will always come when you have a fraction. We don't want to have 0 in the denominator. So we don't want to have that. If we have a square root, we don't want to have negatives inside of there. Also, if we have a logarithm, we don't want negative or 0 in there. So this is, we don't want that. We don't want that. This always has to be positive. That's what we want. So for part A here, we have a fraction, and if you look at the denominator, we just want to see what x value would be bad, and that's where we have the vertical asymptote. So when x equals 5, that denominator is 0, so then that means we don't ever want x to be 5. So our domain would be all real numbers, negative infinity to infinity, but we got to skip over 5. For part B here, we're looking at a log, and so our deal with log is that we want this x plus 5 to always be positive. So we need x plus 5 to be greater than 0. We can solve that inequality and know that that means x has to be bigger than negative 5. So if that's happening, we want from negative 5 over to infinity. If you want to, you could also think about the graph of this guy. The logarithm is the inverse of our exponential function, and so we know that it looks something like this. If we think in terms of transformations, this plus 5 means we would move to the left 5 spaces, and so our basic function has a vertical asymptote on the y-axis. So if we're going to move to the left 5 spaces, we will now have a vertical asymptote at negative 5, and our graph moves over as well. So you can see it will be from negative infinity, or from negative 5 over to infinity. Okay, for question 11, we're talking about solving exponential equations. So this is one of our last topics that we had. So the very first thing, if you have variables that are in our exponent, you want to try and make the bases match. And so when I see 49, I think, oh, that's 7 and 7. And it's a 1 over that, so that's going to be, or can be rewritten as 7 to the negative 2 power. And then that whole thing is to the x plus 1 equals, we already have a base of 7 over here. So now that we have those bases matching each other, well, almost, we have some parentheses that we want to get rid of right here. So we're going to try and make the bases match. The parentheses are kind of in the way, but remember the property of exponents, we can multiply those. That will become 7 to the negative 2x minus 2, because that negative 2 would distribute, is equal to 7 to the 2x minus 3. So now that the bases are the same, then we know that exponents have to be equal. So we can rewrite this as 2x minus 3 equals negative 2x minus 2. Let's try and put our x's together. So we'll add the 2x over. That's 4x minus 3 equals negative 2. Add 3 to both sides. We get 4x equals 1. Dividing by 4, x is equal to 1/4, which you can plug in and double check. But normally with exponential equations, there aren't any troubles, but just if you want to verify that you're correct. Okay, for part B, we have a little bit going on before we can actually try and solve the actual exponential equation, because our base has a couple of numbers that we need to get rid of in order to isolate our expression. So we're going to add 7, so we have 5e to the 4m minus 3 is equal to 20. And again, we're still trying to isolate that guy, so we'll divide both sides by 5. So we get e to the 4m minus 3 equals 4. Now this one's different than the previous problem because our bases are e, which is about that 2.7 number, and 4. There's no way to make those bases match each other. So for this one, we're going to try and make our exponent be more on our regular level by applying log to both sides. So we're going to take natural log of e to the 4m minus 3 and natural log of the right side. Because if both these quantities are equal to each other, 4 is equal to this thing, then natural log of those things is also equal. And as soon as we write that, then we'll be able to take the exponent on the e and bring it to the front. So we're going to have 4m minus 3 times that natural log of e. And that's all equal to natural log of 4. What's kind of nice with this one, because it's a base of e and we have natural log of e, this is log with a base e of the e. That's the meaning of natural log. And so this is going to be equal to 1 because e to the first power is what gets you an e. So if I have 1 times that 4m minus 3, well, that just is going to be 4m minus 3 equals natural log of 4. Natural log of 4 is just a number, so we're going to treat it as such, and we're going to try and get m alone. So we'll plus 3 to both sides. This is going to be 4m equals natural log of 4 plus 3. These can't combine because 4 has the natural log on it. Then we're going to divide by 4. So we can say that m is equal to natural log of 4 plus 3 divided by 4. And this would be our exact answer. We can find an approximation by entering that on our calculator. On my calculator, when I enter this, make sure that you're going to put some parentheses around the numerator before you divide. It looks like it should be about 1.09, well actually 1.1. This would be the approximate answer. All right, going on to question 12. This is just trying to simplify the logarithm. So we're going to use those properties of log. First thing I notice is that there's a coefficient in the front of these logs. We're going to use that power rule to bring them back. So this will be natural log of x minus natural log of y to the 5th plus natural log of z to the 1/2 power. So the property of exponents, or sorry, the property of natural log says that if you're subtracting, similar to the property of exponents, you can write this as division. And then we're adding to that natural log of z to the 1/2. So if it's addition, that turns into multiplication. So we have a single logarithm, because that was what the direction said, of x over y to the 5th times z to the 1/2, which we could write all together as x z to the 1/2 power over y to the 5th as my final answer. And that's simplified. All right, for question 13, those are just solving equations with natural log. So we're going to use those properties a little bit to help us out. So right away, I notice that those two can combine together as natural log of x times x minus 3. Now there were two types of log equations that you could have. One where there was log on everything, which is what we have here. Compared to B, there's not like a log on the 3 or the 13, so that's going to be a different type. And part C also has a number that doesn't have a log. So B and C are going to be similar to each other compared to this one. So for this part A, since log was on everything, we wrote log of something equal to log of something else. And so what that means is these arguments here have to be equal to each other. So x times x minus 3 has to equal 5x minus 7. So we'll simplify this. This will be x squared minus 3x equals 5x minus 7. This is a quadratic equation, so I'm going to move some stuff over here to make it equal 0. And that will be x squared minus 8x plus 7 equals 0. Which we can factor this, or you can use quadratic formula if you'd like, but if I factor it, it'll be x, and then 7 times 1 makes 7. If I make them both negative, that would add to be a negative 8. So it looks like we'll have x is 7 and x is 1. But before we box those, let's make sure they're both okay. 7, if I go and plug it back in, it's okay for all of these. And when I say okay, it means it's not going to make us take log of anything negative. So that's good. Now 1, when I look at 1, it's not going to work in this expression here because we're going to get 1 minus 3, which would be negative 2. So that's not going to work for us. So our only answer here is going to be x equals 7. For part B, since this one does not have log of everything, we're going to try and isolate this log, and then we'll be able to rewrite it in exponential form. So we're going to minus the 3 over. We have 5 log, even though there's not a base, you could think that there's 10 there, of 7w plus 1 equals 10. Then we'll divide both sides by 5, and so we end up that log with base 10 of 7w plus 1 is equal to 2. So again, this one you can't just drop log. No dropping the log like we saw in the last problem. The last problem had a log and a log equal to each other. This one does not. We have a log here and then no log on that side. So what we're going to want to do is rewrite this in our exponential form. So remember, we have 10 is our base, 2 is the power on that, and then this equals that argument. So this is equal to 7w plus 1. So I can rewrite all of this to be, well, 10 squared is 100 equals 7w plus 1. I could minus 1 from both sides. It's just a linear equation at this point. So I have 99 equals 7w, divide by 7, and we have w equals 99 over 7. And then 99 over 7, if I want to kind of just double check that it will work in here, if I multiply it by 7, the 7's cancel, we'll have 99, and then add 1, we're going to get something positive, so that seems like an okay answer. So we're going to say that's our final answer here. You can check it completely, but it's working okay. So then our last question here